Hello, let us continue our discussions of electric fields near continuous charge distributions. Here is a stick of charge, this red object here, and our task is to find the electric field at the origin here, or at that location. And let us define this, let's define this distance as, let's define this as x equals a, and we'll say that this has a length L. Okay, so now notice this this stick has a varying charge density. The charge density varies from it varies as we go along the positive x-axis here. It varies thusly. All right, so here's what we're going to do. Well, we are still going to say that this stick is made up of lots of infinitely small point charges that we'll call dq's. And that dq, that positive, this is a positive charge density, that dq has a contribution to the net field at this location that we'll call dE. It points to the left. Electric fields point away from positive charge. And so there are lots of, again, there are lots of dq's. Here's another one that happens to be closer to our origin. That one has a contribution to the field that is also very small. Let's see how I can draw it. But it's bigger than the other one, than the blue dq, the dE, because, well, this one's closer, right? So what we're going to do is say, well, there is a field that is the summation, the superposition. That's a phrase that can be used to say what we're doing. We are superimposing all these fields. The superposition of all those infinitely small fields. Okay, so, well, we say that our dE's are made by point charges dq's, so we can call this k dq over r squared. And, you know, where these r's refer to, well, here is a vector r locating this blue dq. There's an r. Here's a vector r locating this green dq. All right. Well, these we're going to write as, well, how much charge does dq have? Well, that depends. It depends on, well, how dense is how much charge is there per unit length at that location, and how long is that location? So we can still say that this dq is lambda dl. The big difference between this and a previous example is that lambda is not simply q over L, the charge of the stick. I mean, the stick does have some charge. We'll actually find how much charge the stick has later. But so we can still say, I mean, by definition, linear charge density is a ratio of charge per unit length. Notice I'm going lowercase here, not to say that there is some total amount of, I mean, it's just not a constant. Okay, so what we have to do is now use our expression for the charge density in our integral. I'm going to pull out this k, and we have beta x to the third dl over r squared. Holy mackerel! So we've got lots of different variables here, but guess what? They really all mean the same thing, right? Here's we have defined this as the positive x direction. R vectors point in that direction. DL's point along that dimension also. So we can turn these all into, let's call them x's. How about that? So let's see. So we can say that E is, I'll pull out the beta too. How about that? Look, so we have x cubed over x squared dx. Well, this sure is starting to get easier. Okay, what are our bounds of x? Well, I'm going to say this goes from a to a plus L. So this is just a different style in a previous example where we said this is, in a previous example we said this is coordinate x equals a, this is coordinate x equals b. We went from a to b. Now we're just changing style a little bit just to give you exposure to a couple of different styles of how these are presented. Okay, so this integral did us a nice favor here, and so we get k beta x dx from a to a plus L, or k beta over 2x. So the integral is x squared over 2. I'm only going to evaluate the x squared part. Why bother evaluating the 2 is a constant, so that can come out there. And we go from a to a plus L. And let's see, we can say that's k beta over 2 times, let's see, a plus L squared a squared plus 2al plus x squared, right? That's the top evaluation, minus, here's the bottom, a squared. Yeah? Okay, go on. All right, well, there's an answer. It's not elegant. It is, but I bet it is elegant in some way. K beta over 2 2al plus x squared. What? What am I doing? Ugh. Sorry, this is an L squared, of course. I was like, how could x be in there? L squared. Get out of there. L squared. That's better. Okay, so, what does this say? What does this say? Well, let's see. It's something like, it's something like if, I bet. Yeah, there's some interpretation to do with this result. Pardon my pauses, but that's okay. And if we want to turn this again into a vector statement, I would say it like that. Okay. One thing to do, why not? One question might be like, what is the charge of this stick? Right? So what is its charge? Well, if we want to do that, what's this over here? We could say, let's see, so finding stick charge. Well, how much charge? Well, I don't know. Let's add up all the charges and find out. Right? So what are all these charges? Well, that depends. They are lambda dLs. All right. So Q is, let's see, beta x cubed dl. How about we do that? And again, we go from a to a plus L. Uh-oh, this is going to be a pain in my butt, right? Let's see. So, okay, that's beta x. How about this? Beta over 4 x to the 4th from a to a plus L. I can tell you what I don't want to do, and let's do that. Hang on. Well, I picked a bad time to do this. So let's do this. Let's say, we're going to make our lives a lot easier by doing this. Let's say this stick ranges from, we'll call this coordinate x equals b again, okay? And then we can say, right, Q is beta over 4 b to the 4th minus a to the 4th. And now I feel much better about that. So that's how much charge this thing has. So look, then we could say like, well, look, that's a way for us to say what beta is. Beta is 4q over b to the 4th minus a to the 4th, and we could dump that into here. If I'd done this differently, maybe I'd go a to b here, right? And we'd have a different expression here. And if we had done that, right, let's try. If we had gone a to b here, then we'd have K is, or E is K beta over 2, and it would simply be, watch this, B squared minus A squared, right? But look, here's what beta is. So let's put that in here. K over 2, B squared minus A squared. And here's the beta part. That's 4Q over B to the 4th minus A to the 4th. Do you recognize that B to the 4th minus A to the 4th can be doctored up a little bit, right? We say, let's see, B squared minus A squared. Let's do this 4KQ, right? And then look, this is 1 over, oh look, it's B squared minus A squared, B squared plus A squared, right? Sure. And then one of these goes. I don't feel too bad about that. E is 2KQ over A squared plus B squared. All right, fine. I mean, do you have to do all this? No, you don't have to do all this. The point being, look, I mean, two big points. Here's how we handle, I mean, what we're really trying to get at is how do we handle varying charge densities? Well, we, use the function for charge density, quote unquote, as simple as that. The other thing is, you can find, lots of things by simply adding up the tiny little amounts of them, right? Here we found the charge by adding up all the tiny little charges. Here we found the field by adding up all the tiny little fields. All right. So, as a general strategy, that can be a consistent one. Okay. So, the answers aren't the most important thing here. The process is the most important thing. Okay. Thank you. Uh-oh, this looks ominous. How do I stop?